Good morning. I'm Charles Clark. Real pleasure to welcome Venky back. Many of you know him from his time at the Center for Superconductivity Research at the University of Maryland, the predecessor organization of the Quantum Materials Center. Venky is an alumnus of AT&T Bell Laboratories and of Bell Communications Research, Bellcore. And it was when he was at Bellcore, I believe, that he invented the pulse laser deposition process that turned out to be really revolutionary for its ability to take the ceramic high temperature superconducting compounds that had just been discovered and put them down as thin films on substrates, enabling a whole new field of research. I remember my first meeting with Venky was when I came to visit the Centers for Superconductivity Research, probably in the mid-1990s. He was sort of like an action figure. He had this huge group, a Rutherford backscattering apparatus for analysis. It's like almost a miniature Bell Labs. And he's been very productive and prolific in research. He spent, I guess, about a decade as the director of the Nano Institute at the National University of Singapore. Founded several companies there. He founded a company that's still in business in College Park, Neosera. Maybe some of the students will interview him for jobs later on. It's been commercializing the pulse laser deposition process quite successfully. It's well recognized in the community. Venky received the APS George E. Paik Prize in 2012. And just last year, the Distinguished Lectureship Award on the applications of physics. And he has a new gig now, which I guess is illustrated on his first slide. He's the director designate of the Center for Quantum Research and Technology at the University of Oklahoma, the alma mater of our own Ian Spielman. And so with that, please welcome Venky.
Thanks, Charles. Appreciate it. And it's a real pleasure to be, visiting the alma mater, both Maryland and NIST, of course. And just to give you an idea, I decided to leave NUS by the end of 2018 and gave them notice that I'm going to stay there for one more year, and that's it. And I'm not renewing my position there. And so I came back in 2020 and I took over my company in Maryland, actually, because my CEO had an untimely death in the end of 2019. And so we had to survive the COVID and split the company into two. There's a lot of things that happened in 2020. It was a very busy year for me. And I thought I was going to become we had like a half a dozen small high-tech companies to manage, and I thought I'm going to be in and spend the rest of my life as an entrepreneur. And suddenly this opportunity came up at Oklahoma University to head up this center as a director, and I'll be joining there full-time starting July 1, basically. And but I'm beginning my work there already on a part-time basis. The Center for Quantum Research, there are three things that I look for when I take up a job somewhere. And that is, number one, I want to make sure that that place really wants to go somewhere, that there's a real commitment from the grassroots level to the senior administration level. And I found that enthusiasm here at this place. And number two, you would like to have a solid group of what I call people you can build a foundation on. And right now, the center has already hired a number of people in the AMO and condensed matter area, as you can see. And there's a bunch of emeriti that would be probably will be replaced by a number of what I call younger generation that are coming along. And my job will be to integrate this team with the rest of the university in terms of the engineering and also the life sciences, and bring in some of the really outstanding people into the mix to build a what I would call a dynamic team at this place. And the third thing that I look for is resources, and which is also very good here. There was, if you recall, the building, which is the building that's shown in that you're facing here, is the Lynn Hall, and this was built with an endowment of about $35 million, and it's a brand new building built to NIST standards, and it's and also we have endowment money to hire faculty. We have still several faculty that position that are open, and I've been promised in a year or so further financial support for this moving the center forward. So these are the things that made this very exciting for me to go and take a look at and participate in the growth of this center. Basically, my hope is in 10 years' time would make a substantial change here. So now with that PR part, now I switch over to my actual talk, which is route to low energy memories and brain inspired electronics. And this was the work that was done, and this work started about 6 years ago in Singapore. And the team consists of the student, Sritosh, who is, are you able to see my pointer? Hello?
Yes, we can see your mouse.
Okay, you can see the mouse. Okay. So Sritosh Goswami, he was a graduate student, and this guy is, I have graduated about, as a mentor and co-mentor, about 56 PhDs. And this guy is in the stratosphere compared to any one of them, basically. I have students from Caltech, MIT, Rutgers, Maryland, and NUS. And when I compare him with all of them, he's in a totally different space altogether. And this is Sribrata Goswami, who is the physical chemist that synthesized the amazing molecular system I'm going to be talking about. And so the question now is, what's the rationale for low energy switching energy memory? So let me just go through some numbers with you guys. Okay. So I just, for the fun of it, calculated, how much an average human brain consumes on this earth. And an average human brain consumes about 20 watts of power. If I add up this 8 billion people on this earth, that represents about 1.6 times 10 to the 11 watts, okay, and of power that's consumed. And this makes some fundamental assumptions that, that people at night and day are consuming the same power. That's a simple assumption. And second assumption is that I've neglected our former president out of this equation because these numbers could go totally off wild, basically. So then beyond that, then we come to the power consumed by data centers in comparison. In 2016, you can see the data centers alone consume something like 3,000 times more power compared to all human beings thinking at the same time. Now, if I look at the data centers in 2025, the projection is that 20% of the global power that generated will be consumed by data centers. And by 2045, basically there'll be no global power left to supply the data centers. If we continue electronics consuming power the way it does right now. The good news is 50% of the power consumed in the data centers is actually memory. So if you can come up with efficient memory devices, you'll make an immediate global impact in the way energy gets consumed. Okay, so that's one of the exciting rationale as to why one needs to work on memory devices and see if you can reduce the power of the power consumption of the memories. Okay, so we started working, and we had several approaches, and the first approach is using an organic technology. And so this is a molecule that was developed by Sribrata Goswami almost 30 years ago for his thesis. So this molecule consists of 3 ligands, identical ligands, and this entire group is a the phenyl-azopyridine ligand, and you can see there are 3 of them, 1, 2, and 3, and at the center is the ruthenium atom sitting at the in the middle. And so this looks actually physically like a 3-winged butterfly, basically, if you can kind of picture it in your head. And the real key element of this, or a key part of this whole molecule, is this N double bond N, which is the azo group. And I'm going to come to a little bit more in terms of why that's important. Now, this molecule can be essentially spun on a surface like any photoresist, and we spin it on top of, so here the yttrium stabilized zirconia substrate on which we grow a conducting indium tin oxide layer. And this layer is atomically flat. I mean, literally, I mean, the surface roughness of this indium tin oxide is of the order of like, 0.1 nanometer or better. And essentially, these films are grown by a pulse laser deposition, something that Charles mentioned earlier. Now, this brown layer here is this organic molecule spun on top, and the thickness of these molecules are typically between 20 to 80 nanometers. And then we evaporate gold electrodes on top. You make a top contact to the gold electrode and a bottom contact to the ITO layer. Now you got a effectively that what looks like some kind of a capacitor, but in reality it conducts. And so we measure the transport across this layer, okay, vertically. And this is what you see. And this is where the memristor comes in. So if I look at the current density versus the applied voltage, and this is you can see it's a semi-log plot, right? So this is actually, when you go from 1 to 2, this is actually Ohm's law. This is, if you looked at this on a linear plot, basically you would actually see a straight line here, basically. So this is Ohm's law. You come to point 2, the device switches to state 3, and then there's something like a hysteresis, and then the device switches back down at this point, and then it'll come back up again at the negative voltage and switch to position 4, which will then switch down, come back to position 5, and then we come back down to point 1 again. Now, what really surprised me was Sritosh made something like several hundred, a few hundred devices of different sizes, ranging in sizes from 100 micron down to 1 micron, with a variety of devices in each sizes, and all their data is represented in this one curve here. This shade that I'm showing here is essentially all the data of these 321 devices put together here, and this is the mean data that I see here, which is the solid blue line, and the red stuff is the cloud. But what is impressive is you see that they're pretty much reproducible in the sense that the on to off ratio is so large that in any of these devices would essentially give you the same answer if I were to use it in a circuit, basically. So this extraordinary reproducibility of this device done in a simple university lab environment, impressed the hell out of me. I said, well, we really got something exciting going on here, okay? And so we try to figure out is there a way for us to understand what is actually happening at a molecular level, okay? And it turns out that, it turns out that this, I have to say a few more words about what else is involved in these molecules. Generally, I talked to you about this. This is the three-dimensional image of this molecule, which is the ruthenium-centered phenylazopyridine, or RuPap. And next to this molecule are these two counter ions, which is here, the green ones that I'm showing here. So the actual ensemble is this actual main molecule plus these two counter ions, and they create some kind of a Coulombic equilibrium, the whole system, basically. And these counter ions play a very, very important role, which I'm going to come to in a few minutes, and I'll tell you. And of course, the interesting thing is we can take the same azo group and put them into a slightly different molecular structure, which is shown here, which is an RUTD molecule. And this molecule gives us even more fascinating properties, which I'm going to describe a little later. So what we're really doing here is molecular engineering. In the molecular engineering, we can play with the metal center. We can replace ruthenium with some other metal like iron, or it could be zinc or anything else. And then in addition to that, we can replace the ligand, and then we can also replace the counter ion. And these are the three parts that we play with in trying to engineer the different electronic characteristics that I'm going to be showing pretty soon. One of the exciting things is the Raman spectrum. If you look at the Raman spectrum of this molecule, and you put the molecule in different states, in different switch states, basically, what you see is that there's a bunch of wiggles which don't seem to change whatever the state is. I mean, they're pretty much the same, excepting you come to three peaks here, which are labeled mode 0, mode 1, and mode 2. And there you see there's a lot of dynamics going on. So in other words, when I change the actual redox of the molecule, the change is occurring at these three modes. And these three modes actually correspond to the azo mode, which is the N double bond N. That mode and its vibration properties are reflected in these three different Raman peaks. So what are these three peaks? The mode 0 corresponds to N double bond N, which is what we call state 0 or an unreduced molecular state. And that corresponds to mode 0. So when you're in mode 0, all the molecules are in mode 0, you will have a very large peak at 0 mode. Now, when I go to state 1, I am 1 electron reduced, okay? And that corresponds to mode 1, which is state 1. That's a Raman spectrum. And then when a 2 electron reduced, then you get state 2. So by just looking at the Raman spectrum, you get immediately a picture of what is the redox state of the ligands and how does it correlate with the actual switching characteristics, okay? So now let's look at the actual electronic characteristics and look at the corresponding Raman spectrum for each one of them. So let's go to state 1. Right now in state 1, when I look at the Raman spectrum, what I see is that there's 1 unit on the 0 mode, and there are 2 units under 1 mode and nothing under the 2 mode. So the molecule is actually in 1, 1, 0. So that's what it really means, 1, 1, 0. So there are 2 1s and 1 0. Now let's go to position 2. I crank up my voltage, I get to position 2. Now what has happened is the 0 mode is doubled in size compared to the 1 mode. And so now it is 0, 0, 1. And now when the device is switched to the on state 3, and if you look at the Raman spectrum, everything is under the 0 mode. That means all the 3 ligands are in the 0 state. Now let's come to the negative side at position 4, for example. What you see is all the peaks are under the 1 mode now. That means this position 4 corresponds to 1, 1, 1. And when you go to position 5, you essentially get the 2 peak appearing. And this is the 1 peak at 2 units and 2 peak with 1 unit, which corresponds to 1, 1, 2. So with the Raman spectra, you immediately know beautifully what is the redox of the molecules at any position in this electronic spectrum. What you notice immediately is that in the on state, where the resistance is lower, basically by a factor of 1,000, basically, you see 0, 0, 0 or 1, 1, 1. And in the off state, what you see is that you see 1, 0, 0, 1, 1, 0, 1, 1, 2. And what you notice is the off state has non-equivalent redox states. That is, the molecule, the 3 ligands of the molecule are not in identical states. At least one of them is different. Whereas if you look at the on state, you see all the ligands are identical. So this tells us an idea of what is actually happening. Why do we get this on state and what do I get the off state? And that has to do with the fact that imagine there's a bottom electrode and then there's roughly about 40 layers of molecules and then you have a top electrode, okay? And so I inject electrons from the bottom metal. The electrons hop onto the first molecular system. Then the electrons will now hop from the first molecular system to the next molecular system. Now the electrons hopping probability from one ligand to the next ligand in the other molecular system depends on whether the ligands are identical, because then the so-called LUMO levels line up beautifully. If they're identical in the same charge state, the LUMO levels will line up. If they're in a different, say for example, 1 to 0 is not allowed and 0 to 1 is also not allowed. 0 to 0 is easy, 1 to 1 is easy. So you can clearly see right now when all the molecules are in identical states, the hopping probability is much higher than when they're not in identical states. So just to give a rough number, right? If this molecule is 0, 0, 0, and there's a certain probability for the molecule, the electrons to hop through this entire molecular system. When I come to this, in a 0, 0, 1 system, the probability of hopping is roughly 2/3 that of the 0, 0, 0 system. But since the hopping is like over 40 molecules, 2/3 to the power of 40 becomes a very small number. And that's why the conductivity in the off state is 1,000 times smaller than the conductivity in the on state. So this gives us right away. So that explains us why I get this on and off state. But then why do I get this hysteresis? And the hysteresis has got to do with the counter ion. Okay. So what actually happens is
Venky,
yeah.
Before you go on, could you just go back to that previous slide? This is
Sure.
Bill Phillips.
Yeah.
So I've got two questions. One is, can you give us some idea of what the time scale is for the switching that happens? You've shown us in that central upper central picture what I guess would be what would happen if you went through this process slowly. How fast can it happen?
Yeah, well, it's a very, very good question, and it's actually still a central experimental challenge for us. In fact, that's one of the experiments that I want to do in the next 6 months, hopefully at NIST actually, to really measure what is the intrinsic switching speed of these devices. The fastest we've been able to switch these devices today is of the order of about 5 nanoseconds, and that is purely limited by the fact that we're using twisted, like basically a circuit which is really not designed with a 50 ohm kind of termination and so on. It's really a crude setup. And if I calculate the RC time constant of these devices, I anticipate the switching time to go into something like 500 picosecond or even better.
What determines what the switching time is, or what limits it?
Well, I think it's the switching time will be purely limited by how fast you can move the electrons in the system, really. And you can see, first of all, that these are ultra thin layers, right? They're like of the order of 20 to 60 to 80 nanometers. Between 20 and 80 nanometers is the thickness of these layers, and it would be limited by effectively the RC time constant of the system.
Okay. Now the other thing is, I look at these 5 different states.
Yeah.
2 of them you've designated as being on, and 3 of them as being off. There's a lot more possible states for 3 things that could be in 3 different states. So yes. Why have you restricted it to these 5?
Yeah, well, basically, in this particular system, I mean, again, I will show you some data later that by using the right substituent in the system, actually, in the negative direction, we can actually go on to create even more states. For example, like you could say, like a 2-2-2 state would be possible too, right? So those kind of states are achievable in a different molecular system. And is your question even more between like where the region is sloping, where there could be different other on-off values? Is that what you're hinting at, or?
I have no idea what I'm hinting at.
Okay. No. Okay. So I think your question is more to do with, for example, you have 1-1-1. You can also have a possibility of 2-2-2, for example.
For
right?
example.
I mean, yeah, exactly right. So in order to get 2-2-2, you'll have to go to even more negative voltages because I have to really, take out more electrons, right? So that means I have to go even more negative, and doing that, sometime in this particular molecular system, the device breaks down roughly around about -6, -7 volts. But if I did this with a different molecular system, we actually can go pretty negative, and we see those states actually.
And permutations around this triad don't matter, or do
No,
they?
it doesn't matter. It doesn't matter.
Okay, thanks.
Okay, great. Okay.
Can I ask a question also?
Oh, absolutely.
So I guess So the picture here is that basically the tunneling is different between these two states, and so it's harder for electrons to get across. And so does that mean there's really an intrinsic coupling in this device between the resistance and the on-off ratio, that if you make the layer thicker, then you'd get an on-off ratio, but an overall like higher resistance? Or
Yeah, the more the number of molecular layers, the larger the on-off ratio would be. Okay, that's absolutely true, but there is a limit to how thick this layer can be, because at a certain point we find that the switching doesn't take place anymore. Basically, there is a limit to the thickness, and that's why it's about 80 nanometers about the thing. And the exact root cause of why this happens is we still haven't figured it out completely in a satisfactory way, but there is the limit to the thickness of this device. This is that's why we work between 20 and 80 nanometers of this device. Right? Okay, we can go even thinner actually. And all right, so now the history.
Could I ask one question?
Sure, Charles. Yeah.
About the role of the ruthenium ion. Is
Yes.
it just is any other transition metal with comparable valency going to work as well? Is the ruthenium there to sort of stabilize the overall molecular geometry, or do aspects of its electronic structure come into play?
Well, you see, there are essentially the coordination number for ruthenium is equally very important. It's a hexafold coordinated system, ruthenium, And so what happens is each ligand is attached to the ruthenium in a bidentic structure. That means there are two places where the let me show the molecule actually here. Right, you can sort of see the ruthenium attached to this nitrogen and this nitrogen. It's like a bidentic structure, and this is actually very important. And I personally think that this ruthenium gives this molecule an amazing physical stability, actually, in the structure. The actual ruthenium valence itself doesn't change at all. Ruthenium valence exactly remains what it is. It's in the two state and doesn't change at all, basically. But on the other hand, the chemistry of ruthenium gives this molecule phenomenal structure, rigidity, and stability. And that's one of the reasons why the device data is so reproducible, and it's just pretty amazing. I'll show some more data in the future, which makes its molecular structure remarkably stable. For example, we can take these molecules, we can heat them in vacuum. Take this device, we can heat them in vacuum to about 600 centigrade, and then we bring them down to room temperature, and then make the device measurement, and nothing changes. It looks the same. I mean, I this completely blew my mind. I said, this doesn't make any sense to me. I mean, I get oxides that I make, which we'd get crapped up if I heat them up to 600 in vacuum, and these things are so stable, right? And so there's got to be there's something magical about this ruthenium that it really just offers the stability here, and so. So the hysteresis is obtained because of these counter ions. And what the counter ion does is, every time the redox changes on the ligand, the counter ion moves to a slightly different spatial pocket. Okay, and those pockets are defined by effectively the electromagnetic interaction between this molecule and this counter ion. And this is sort of like a ratchet in a wrench, basically. The inertia of this gives you this hysteresis curve that we get. And you can see we can control this hysteresis by varying this counter ion. If you make a light counter ion like chlorine, PF6, you get a hysteresis that goes like this. But if I have a more sluggish ion like BPH4, which is boron 4 phenyl group attached to it, that becomes very sluggish, and so the hysteresis become much narrower here. Okay, so this is the way we can engineer the memory characteristic, the details of the memory characteristic, by playing with these counter ions, actually. And now something extraordinary happens when I change the local field in the molecular structures. Okay, so we create 3 types of devices. So this is what I call device A, where I have a broad electrode on top, broad electrode at the bottom. So these electrodes are large area electrodes. Now I take device B, where on top of the indium tin oxide, I evaporate a bunch of gold nanoparticles. And these nanoparticles are the size of, let's say, 30 nanometers, 30 to 50 nanometers. And they cause local field enhancement. Now I do a third structure where I bring a conducting AFM tip and position it right over the molecule on top of, let's say, which is sitting on top of a gold nanoparticle. So you can sort of see that in the first structure, there's no field enhancement. In the second structure, there's significant field enhancement at the bottom electrode. In the third structure, I have field enhancement both at the bottom and top electrode. Now see what happens to the electrical characteristic, okay? I mean, this is absolutely remarkable. This is essentially the large area electrodes, and you can see the switching voltage is roughly about 4 volts, and the current density is like about 10 to the 2. And now when I go to when the field is enhanced at the bottom, now suddenly the switching voltage drops down by 1 order of magnitude to 0.4 volts, basically. And then the amount current increases. And finally, in switching device C, you can see that the turn on voltage drops down, close to 100 millivolts, and the current density goes 10 to the 6 amp per centimeter squared. This is absolutely mind-blowing and remarkable. That what is really beautiful thing about this is, right, ultimately I want to build small devices, right? So in fact, these are patterns made at NIST by Rob Illick, and he made these for me in the CNST clean room. These are bottom electrodes ranging in different sizes, 100 nanometers, 500 nanometers. And you can see that the molecules, and the data is now obtained using a CAFM tip, and by 150 millivolts, this entire the device has been completely switched on. Whereas the molecules in between here is completely in the off state. Nothing happens to it. And I have to go to much, much higher voltage, 450 to 850 millivolts, before I can get the region in the middle to switch on, right? So this is actually very good news. What it tells you is the smaller I make my device, the better the switching characteristic of these devices are. And which is like one of those few what I call serendipitous or fortuitous event where things are working to your advantage, actually. So this is a very, very exciting development of this molecular electronic device. One of the things that people worry about in this memristor type of devices is, like, in terms of reproducibility, what is your statistics in terms of on current and off current? And you can sort of see these are literally separated by 3 orders of magnitude here between the on current distribution and off current distribution, which means that if you build circuits with millions of devices or, a billion devices, the probability that you will have an error is like a part in 10 to the 13 or so, which is, remarkably, error proof in terms of large scale device fabrication and scaling up. These are some of the what I call stability characteristics, where we do a switching, where we do a write, then a read pulse, and then an erase pulse and a read pulse, and we just repeat this cycle, and this is the measured current here, as you can see. And we measure this as a function of looking at all the different states. And this is repeated many, many times. Okay, this is how you try to determine how good is your memory. And this is a very important step to see how many cycles can you do before you start losing the memory states. If I did this experiment with, let's say, a flash thumb drive, like a thumb drive memory, by the time you get about 10 to the 6 cycles, your thumb drive will start generating defects, basically. And you can see this memory, I'm going up to about 10 to the 12, and it still hasn't crapped out. It's still going on like the everyday bunny. It just keeps on and on. It keeps going. And this is truly a remarkable result for an organic device. And this is actually data, stability data, done at 350 Kelvin, which is about 80 centigrade, looking at the on state and the off state, how robust are they? And this is a period of about 3 months in total time. And you can see that the on state and the off state hardly show any deterioration in their conductivity values. And so I was desperate to compare this with some, ITRS roadmap. I call up my friends at Intel, and they all say, "Oh, we don't make ITRS roadmap anymore because nobody knows where the hell the roadmap is going." So finally said, "Look, guys, give me something in. What do you have in the memristor roadmap?" Well, the last one we have is 2015. So they sent the stuff to me, and I said, "Okay, let me just put this and compare. Where does this stand with respect to our competing organic devices, for example?" So read current for an ITRS projection should be greater than 10 nanoamp. We have achieved values as high as a microamp, and the best organic device that we've seen so far is about 200 femtoamps at 400 nanometers squared. Write erase time is of the order of nanosecond. Right now, we achieved, this number has been measured now down to about 5 nanosecond. I think the actual number is probably like 0.5 nanosecond or better, but it needs to be demonstrated, basically. And the best organic device next is on the order of millisecond. Write cycles needs to be greater than 10 to the 10. We have demonstrated greater than 10 to the 12. And, forget about these guys. Write voltage should be less than 0.6 volts. Right now, we are down to about 0.12. I'll show you some even better data. And read voltage, again, should be less than 0.2 volts. We are now approaching basically 50 millivolts. And write energy should be less than a picojoule, 450 attojoule. So the devices work from minus 40C to 80C, which is typically the temperature range in which the semiconductor devices are expected to work, okay? And so now, this is what I call a champion device that we made, and this has got again an on-off ratio of 1,000 or so, and this is essentially a CAFM tip right over a gold dot, and so the effective area of the device is about less than 50 nanometers squared, which means it's a device with a effective side of about 7 nanometer, basically, and so the switching energy in this particular case comes to about 1 attojoule right now. I mean, my suspicion is this number is more like 0.5. So this number is more like a 0.1 attojoule, but that is, to me, a pretty astounding number for a memory device today, I mean. And so there's a lot of work we've been now doing in terms of playing with electrodes, top electrode, varying them. So by varying the electrodes, you can show that the scaling with respect to the work function of the electrode to some extent. And of course, again, trying to create nanostructures and of course, bottom electrodes, all of these stuff. I mean, we begin to understand more and more of how these devices are working, okay? The switching uniformity is very important. The competing technologies, oxide-based memristors is a competing technology. Companies like Samsung and many others are investing very heavily into it. And even TSMC is now getting into oxide-based memristors. Now, the thing is, the switching uniformity in oxide memristors is not that good because the switching mechanism in oxide is due to what's called a filamentary mechanism. And because of that, at the nano level, basically, the devices have tremendous stochasticity. Whereas in our devices, basically, this is a device A, this is another device I'll mention in a few minutes later, which has got multiple states. The uniformity of switching is absolutely phenomenal. I mean, there's absolutely no filamentary, nothing. It's literally a molecular mechanism. So we can actually create, essentially, these are conductivity maps that we have created, structures, and we can essentially do patterning down to about 7 nanometers type of dimensions that we can switch, basically. And the actual molecular diameter is about 1.5 nanometers, which, okay. So now we're almost within, essentially 4 to 5 times the molecular diameter of the actual molecule, basically. So we come down to that level. How about the switching mechanism? If you use something like, essentially tunneling enhanced Raman spectroscopy, which enables you to measure Raman spectrum from extremely tiny areas, basically. So we can now get down into where these gold nano dots are, and we can go very close to those nano dots and look at the Raman spectrum in the on state and off state. And the mechanism is exactly the same. The on and off state mechanisms are exactly like in the bulk case that I showed you. The same kind of switching mechanisms are happening even on the nanoscale. So this is a real proof that this mechanism here is purely molecular in nature. And therefore, the ultimate limit, the device size limit, is going to be approaching something close to 3 nanometers, which will be roughly twice the diameter of the molecule. And we don't know. We may even approach the single molecular case. It's possible, you know. And now something amazing happened. We took these devices and varied the temperature, and in a certain temperature range, we started seeing some amazing phenomenon. And that is, you see 3 hysteresis steps for a 16 nanometer film. You get this beautiful 1 hysteresis, 2 hysteresis, and 3 hysteresis. And this was completely amazing to me. What is really going on here? So if I take a 16 nanometer divided by 3, you get a number like 5 nanometers approximately, okay? So keep that number in mind, okay? Now let's go to a 43 nanometer film. Now you get 8 hysteretic steps, 1, 2, 3, 4, 5, 6, 7, 8. And again, 43 over 8 is, again, 5 nanometers. 64 nanometer film gives you 12 steps, and again, 5 nanometers. So what is really happening is essentially 5 nanometer represents 3 molecular layers, basically, 1.5 times 3 approximately, give a little bit space between them. So 3 molecular layers of switching. So essentially what is happening is I switch the molecule, then I'm independently switching 3 molecules, another 3 molecular layers, etc. So you get 3 molecular layers, 3 molecular layers, 3 molecular layers. Here, again, 3 molecular layers, 3, etc. So I said, wow, this is truly amazing. Why are we switching 3 molecular layers? It's because we're using a counter ion like PF6, which is a little bit big, and that counter ion is moving, changing spots every time the molecule switches, and it's pushing the molecules above and below. So 3 molecule layers are switching, okay? So then we said, if that's the case, if I make the counter ion really small, like chlorine, what happens? Now you see, this is a small counter ion, so it doesn't affect the adjacent layers. Now what happens is a 12 nanometer film gives you 8 switching steps, and a 44 nanometer film is giving you 29 steps, which means I am literally switching 1 molecular layer after another. Now, what is really astounding about this is this entire film is spun-on film. So I expect this film to be a completely an amorphous, crappy layer, basically, right? But somehow the film is self-assembled and such that I'm literally able to switch these molecular system 1 layer by layer after another. In this case, I'm literally switching 1 molecular layer, another molecular layer, etc., which is, I've never seen anything like this. This is truly a remarkable phenomenon. And we're still trying to figure out how and why this is actually happening. If there is a way, using some X-ray scattering technique, can we actually show the self-orientation of these molecules once they are switched on, and that this thing actually happens as a byproduct of that stuff? And why that happens still needs to be figured out. But there's a lot of very interesting new phenomena taking place in this molecular system. So now I want to now talk about, neuron-like devices and why are they really important? I mean, if we really look at what's happening to our society, our life, what's happening now, the biggest freight train that's headed our way is AI, artificial intelligence, and machine learning. I mean, this stuff is literally going to dictate our life for the next, several decades. It's sort of the equivalent of, James Watt's steam engine. Let's put it that way. It's one of those really fundamental kind of thing that will have a huge impact on our society. So for executing AI ML type of software, of course, now, companies like Intel is bringing out the Lowy series chips. IBM has got the True North chips. So every electronic company is introducing their own so-called bio chips, but they're all based on CMOS logic, which is still limited by, the von Neumann bottleneck and all the stuff. So you need really a neuron-like device, and there's a real rationale for it. And this is the time which is ripe to develop these technologies. And that's why we're very interested in this stuff. A neuron, to me, is the most amazing technology that there is. Okay, it's so incredibly complex. My prediction is in the next 100 years, we'll still never be able to reproduce an artificial neuron. which does all the things that a neuron does. I mean, the neuron is truly a miraculous thing. I mean, so you have neuron, this big head is called a soma. It's your central processing unit. And it's got this very large axon with which it, communicates with the other neuron. And then you got all these dendrites that bring in information from all its surrounding neighbors, okay? And then all these informations are processed by a central processing system. Then eventually the output of the neuron goes out through your axon, which then communicates with the dendrites from all its neighboring neurons. So this is a very complex, tangled up system. And there are several amazing things about the way neuronal communication occurs. Unlike CMOS, where you have digital pulses of ones and zeros, we have actually spikes. And lots of questions are arising today. Is a spike just a substitute for a pulse, or is a spike a packet of pulses? In other words, the shape of a spike has also information in it, right? So these are all questions that are coming up now. Completely asynchronous system. There's no timing at all, no three-terminal devices. And the thing that I think is going to be the biggest challenge to emulate a neuron is that it gets 10 to the 4 inputs per neuron. I mean, in a circuit, how the hell do we make 10 to the 4 inputs to any point? I mean, maximum 6 interconnects, and and even if I do like 8, 2 of them I'll dedicate for power in and power out, basically. It's really a big challenge. This is where optical interconnects may become important for broadcasting and so on. And the axon itself is a lossless transmission line. And how do we build something equivalent to that? And the signal along a dendrite, for example, the information that comes in the dendrite is dynamically processed, and because there's a weight function assigned to them, so it's very complicated. And the synapse is essentially the component where the actual communication actually occurs to the synapse, and that is effectively the building block that everyone is trying to simulate electronically, using a variety of neuromorphic, devices. They all try to eventually simulate the synapse, basically. Now, what is really interesting is the field of this whole neuroscience, developing, understanding neurons and so on, has been going in parallel with electrical engineers doing their own stuff, biogas doing their own stuff. And the consequence of it is that the first model of the neuron is developed by Hodgkin and Huxley. And these two guys took the neuron of a giant squid, and this actually produces a neuron that's roughly about 1/10 of a millimeter that you can actually physically handle in a lab. You can put contacts to it and you can make measurements on it. And these work were done in the the 30s and the 40s of 1930s and 1940s. And this was the model that the circuit model that they built. And this model has not changed over, whatever the last 80 years or whatever, it's remained the same model until a guy named Leon Chua who comes along and he says, hey, we'd like to replace these variable resistors, which represent the potassium and sodium channels. I'm going to replace them with memristors. And he puts his memristors there. And this is the memristive Hodgkin-Huxley model. And this has been the biggest, what I call, breakthrough in this field. I mean, it just goes to show how electrical engineers and so on really need to get involved with the bio guys, and we really need to develop a strong interdisciplinary program to make progress in this area. So Stan Williams, for example, who was at Hewlett-Packard and now he's at TAMU, Texas A&M, they demonstrated an oxide-based, essentially a neuronal type of device, which has got a negative differential resistance. So the idea was that if it's a negative differential resistance, you can actually get gain in the system. So you can essentially see a thresholding behavior where a signal which is below the threshold will not get gain, whereas anything just above the threshold will be amplified. So this is super threshold signal. You can see the output is huge. Sub-threshold is really very, very small, this kind of device. In fact, he went to build, using memristors and capacitors, they were able to build actual neuristors and demonstrate you can get these oscillatory patterns which are typical of, let's say, neurons and so on, and they were able to replicate all of this stuff. They were able to show these things. Now, what I want to show is we have, with our organic memory, we went to a different molecular system, which is essentially the same ruthenium now, but unlike the prior ligand that I showed you, I have two ligands now, but each ligand has now got two azo groups in it. And this is a very interesting molecule. When I take this molecule and do the same experiment, spin it on, I get this very interesting characteristic. Okay, essentially, I get three switching states here. You know, this state and this state. And if you do the Raman spectrum, we actually get a very interesting conclusion that this corresponds to adjacent molecules being in the 0, 0 state, 1, 1 state, whereas here the adjacent molecules are in, one is in the 3 state and 1 state, which is really completely different charge state. So what that means is, in this particular case, there's a very large electric dipole there. Okay. Now, there are a lot of other interesting questions. Does this device also show field enhancement behavior? Okay, yes. For example, if I build a similar structure like I did with the other one, you know, where I have a large area, a high field at the bottom, and high field in both top and bottom, and sure enough, I can reduce the operating voltage down to in the 100 to 200 millivolt range, basically, for the switching. And the current densities can again be approaching, you know, megamp per centimeter squared kind of numbers. Okay, so the same thing can be repeated here also. But this device has some very, very interesting properties. And it turns out that by looking at the Raman spectrum in this device, we can actually show that the totally switched state is one where we are looking at two adjacent molecules, and these are in the 0, 0 state. This one is in the 1, 1 state in the middle case, where in the middle switch state. On the bottom state, which should be a 2, 2, instead disproportionates into what's called a 3, 1 state, which is very interesting kind of thing. And this phenomenon is called charge disproportionation. And then high TC came along, and high TC was followed by colossal magnetoresistance. Man, charge disproportionation was a big deal. Everybody got so excited about charge disproportionation, which is like it gives rise to the lowest energy state is not the one that you thought was an obvious one, but something completely different. And that's exactly what in this particular case. But what is really remarkable about this charge disproportion state, 3-1, is that, you know, let me just skip some of these things. I don't want to get into too much detail. Is that if you look at the charge disproportion state, there is actually a very large molecular dipole. So if I look at the relative permittivity, you can see that I actually get a hysteretics in the charge. Or in other words, essentially, there's the capacitance in this device, and there's a mem capacitance. Instead of a memristor, it's a mem capacitance. So I have in a device both memristive characteristic and mem capacitance characteristic, which is really pretty amazing. I mean, it's never been demonstrated before. Now, if I take this device, and with this one single device, I just put a resistive network outside by varying the resistors and changing the load line, I can simulate almost all the biological specimens. This is actually response of a self-oscillation, which is typical of a neuron, basically the neuronal self-oscillation that you can see here. Or if I put it in a different load line, I get an oscillatory pattern, which is exactly that of a cardiac myocyte. Your cardiac cell has an oscillatory profile, which is exactly like that. It's a very fast drop here, and then there's a gestation period, and then comes back down. So I can actually simulate a heart muscle or a heart cell this way, in a cardiac cell this way. And then the neurons do all kinds of interesting things. They do what is called integrate and fire, where a neuron accumulates signals from many, many neurons, and then it reaches a certain threshold, and then it'll fire. So this is the input to the neuron here, this particular case, our device, and then it integrates at a certain point, and it reaches a certain optimum value, it fires. So you can see, and this I can control by changing this resistor. I can change this time delay by the number that I want, basically, you know, but clearly. And here's another example called potentiation, which is again, the neuron remains, you know, essentially dormant until it reaches a certain amount of signal, and then it becomes active all over again. You know, so these are all neuronal features that we can demonstrate, and we can get, for example, self-oscillations in this device, which by adjusting the load line can actually lead to chaos. Exactly. And in fact, chaotic behavior of the neurons in our brain is a very, very important aspect of our normal brain behavior. In fact, the certain amount of chaos is inherent to the way our brain neurons function, because if our neurons in our brain get into a coherent state where they all start working together, then you get phenomena like epilepsy and things like that. In fact, having a bit of chaos is very, very important for our mental health, actually. And so that's about the neuronal part of it. Then with these devices, we've been able to demonstrate gates and so on. And so, for example, NAND, NOR, and or etc. So we can even demonstrate an adder. And so what we're discovering in this molecular system, to sum it up, is that this system is very, very unique and a completely different approach compared to CMOS or even oxide memristors. It gives us a completely new angle and a way to work with in this system. Okay, so this is the part about the organic approach in my work, and we're also doing oxides and using oxides to build memory devices. And so I'll now talk about the oxide work. Actually, I'm most known for my work in oxides, and this organic thing turned out to be sort of like a digression, but now it's become our main obsession, basically, which is interesting. So tunneling electro-resistance, I'm going to talk about. So it's like a change in topic. If you want to have any questions on the previous topic, I mean, this would be a good time so to raise some questions if you want to. How about you?
Yeah, actually, Venky, we're getting near the point where we do just have discussions. So could you
okay, why don't I wrap it up in okay, why don't I say okay, why don't I wrap it up in 5 minutes? Can I have 5 minutes? How's
sure.
That? Okay. So what let me tell you quickly what happens in tunneling electro-resistance, okay? Essentially what it is we take a conducting substrate, put a ferroelectric layer and a metal layer. Now everything is grown with atomic level precision, okay? This barium titanate, which is a ferroelectric, is actually growing layer by layer, atomic layer by layer. Our control on this growth is like 1 unit cell, basically. So when you take these devices, they give you, if I look at the exactly similar like I did before, resistance versus voltage, I get this type of hysteretic curve. And again, this is a memory, right? What we've discovered is that I can take these devices down to 1 unit cell of a ferroelectric, and I can get an on-off ratio in 1 ferroelectric unit cell, which is never been done before, which is pretty remarkable. So that's the most important part of this data. So I'll pass on to the last part of my talk, which is really, we're not trying to do actual live neurons, and I want to build an actual live neuronal circuit. The question is, neurons grow everywhere. You have no control on them. So we have developed a very cool idea where we create material libraries, and we look at growth of cells on material libraries. So here is the human neuronal stem cells, and I'm growing them on a binary library. One end of the library is actually yttria, the other end is zirconia, and you can see that the cell counts, growth on this end is 0, but on this end is much, much higher. So what it tells you is that the cells love to grow on certain surfaces. They do not like to grow on certain surfaces. So I want to use this technology to restrain where the cells grow on a given surface. Why is that important? There are companies like Neurosyntec. These companies want to use neurons to do use the neuron's ability to sense things like various sensory neurons and put them on a circuit, and then actually connect them electrically to these neurons to the circuit below. Therefore, I can use the sensory property of the neurons in for, let's say, bomb detection, for various things. And they want to use these real live neuronal thing. But you can see what happens to the neuron. When they grow the neuron, they're all over the place, right? They're just like a mess, right? And they really want to put the neuron exactly where the terminals are, etc. So this is where our technology of using, selective growth comes in, and we are working with them on this thing. So that's all I wanted to say. So let me just thank Sritosh Goswami. He's the genius behind his molecular system in terms of using it for memristors. Sribrata is the person who really synthesizes molecules. I want to thank Stan for leading us into this neuromorphic field, and Damian Thompson did all this molecular calculations to so make us understand why things work the way they do. So thank you so much. I appreciate, I'll be happy to answer any questions now.
Zoom applause, and so the floor is now open for more questions.
So I was struck by your reference to the ITRS, International Technology Roadmap for Semiconductors. That used to be sort of a Bible for various parts of NIST management, but I realized I haven't heard about it for years. Is that activity lapsed, or has it been superseded by something else?
No. See, when the ITRS roadmap was active, right, there were probably something like about 50 semiconductor companies who were active, right? I mean, you heard of you heard of companies like Harris Semiconductors, Xilinx. I mean, you name it, and a whole bunch of companies are there. We're all manufacturing CMOS chips, right? Today, the market is consolidated, really shrunk down, and if you look at really front-end semiconductors, right? I mean, there's literally TSMC and Samsung. That's it. Today, these are the only two guys who can go below 7 nanometers, basically. Nobody else can. Even Intel can't. Intel gave up, right? 7 nanometers. So the world has become really consolidated like crazy, right? I mean, so, to stay on the Moore's law curve, right, it's not easy anymore, and it's incredibly expensive. It used to be that when you went on the Moore's law, right, every time you went from one node to the next node, right, you bought not only circuit density, that is the number of transistors per unit area increased, but also the price per transistor dropped, basically, right? So you got gain in both ways. But now when you get to 7 nanometer scale, right, the price per transistor is not dropping. It's actually remaining constant, and in fact may go up if you go to even smaller dimensions. So the question is, it may be economics that may kill Moore's law, not quantum mechanics, basically. And so, where is the real innovation and discovery going to occur? In the semiconductor industry right now, the biggest discoveries and inventions are going to take place in advanced packaging, basically. How do I create more circuit per unit volume, and therefore you want to go into 3 dimensions, basically, and that brings its own challenges. And so, that's where a lot of the innovation is taking place, like that's why the through silicon vias, and then they call, the fan out technologies. These are all completely new technologies that are emerging in the semiconductor industry right now. Yeah. So because of all of these factors, there is no unison in terms of a semiconductor roadmap anymore, because, people are not clear which way everything is going, right? Are you going to focus on making chips? Or are you going to focus on advanced packages? Which way are you going to go, right? TSMC just recently announced 2 very large advanced packaging fabs in Taiwan, just in the last 2 months, basically. So it looks to me like advanced packaging is winning right now. I mean,
Electronics industry effort and a roadmap of that type.
yes.
Did you follow that? And has a similar sort of consolidation occurred?
In the optoelectronics industry? Yeah, I would say so. Yeah, I mean, many of the optoelectronic companies got bought out like crazy. There was a significant consolidation in like JDS Uniphase, for example, used to be a company selling helium neon lasers. And all of a sudden the company became like you just went around buying companies left, right, and center, and it just like grew tremendously. And I mean, I don't know where all those things stand right now, but it's been a significant consolidations there.
Thank you. This is Bill Phillips again.
Hi, Bill.
I wanted to make sure that I understood this this thing about the self-assembly.
Yes.
Now, if I've understood correctly, what you concluded was that when you spin these things on,
right,
instead of going on in a kind of a random way, it self-assembles. But I mean, we're all familiar with self-assembled monolayers, but what you're telling us is we've got like self-assembled 20 layers.
Yeah, I mean, and Bill, I mean, what's really remarkable about this is, right, this phenomenon works only if I made my indium tin oxide layer atomically flat. In other words, we grow this by PLD process, and this ITO layer is like, its surface roughness is like, zero point 0.1 nanometers. I mean, it's really very, very flat. Okay. Now, what we do is we just make it is slightly rougher, the surface, right? So that it's instead of zero point 0.1, it's, let's say, 1.5 nanometer, just produce that roughness. This
Yeah.
effect goes away. We can't
Wow.
see it anymore, right? So really, we need an atomically flat surface to make this work. So this is why I was convinced that's why when this data came, like, we are switching 3 unit cells because the PF6 was the counter ion in this case. So the PF6, when you switch from when you go from here to, let's say, this place here, the PF6 changes position. So what it does is it's a bigger counter ion, and therefore it affects the layers above and below, and therefore we end up switching 3 guys instead of one
Yeah.
layer. But when I get to this guy, here I've replaced the PF6 with chlorine, which is very, very small counter ion. Then its motion doesn't affect the layers above and below, in which case now I'm just switching only one molecular layer, basically.
Yeah. And there's nothing special about the way you spin these things on. It's sort of
no, nothing. See, what it is this molecule. There's a tremendous amount of electrostatics that is taking place, which is governing the molecular orientation, the charge transfer between the molecules, all of this stuff. It's a very, very fascinating system, actually.
Wow.
One of the things that we noticed was when we put these molecules and we did Rutherford backscattering to measure the actual molecular density, we found that the actual spacing between the molecules was a lot larger than I actually anticipated. That there's a lot of free space between the molecules for some reason. And that is probably what is enabling it to do the kind of things that it's doing, basically. It's not topologically confining it's not self-confining itself, right? It is kind of able to move around freely in space somehow, and these electrostatic interaction between them are leading to this self-alignment. I'm looking for ways to measure this by NextSAFs or some such technique, and it's really needs a world-class expert of some sort to work with on this, basically. So
now you speculated about that you might be able to make devices that were single molecule devices.
yes.
If you did that, how fast would they be, and how much energy would be required to switch them?
Well, these devices, I'm absolutely convinced. I mean, we can get down into, I'm think something like 100 zeptojoules, basically. I mean, like essentially, we can get into 0.1 attojoule with these devices.
Okay,
I mean,
how does that compare to KT?
I think KT is still, we're still far from KT, right? KT, I think, is like closer to 10 zeptojoules, something like that. I mean, we are closer to that, right? So we're still an order or two away from thermal energy. So we're still okay. Yeah.
Well, okay. Or, I mean, the next question I was going to ask was, is there any chance of making these things into qubits?
See, that is the whole thing, Bill. I mean, this is the part, right? Right now, I mean, I'm trying to wrap my head around the whole concept of quantum sensing and what the hell do people really mean, kind of thing, the stuff. And this is exactly, I'm absolutely, if there's a way I can work with you guys to come up with qubit concepts, the guy who's synthesizing these molecules is an absolute genius. So right now, my proposal is, right, I'm bringing this guy Sritosh as a research scientist to work at NIST, starting this July, basically. So and the person who synthesizes molecule, he's going to set up a chemistry lab at Oklahoma, and he's going to be making all these molecules. And my hope is to interact with the quantum community to see how can we really, make use of the quantum aspect of these molecules to eventually take into producing something like a qubit. simply because of the extraordinary reproducibility of this system. And it's something that we can really utilize, and it's so easy to synthesize and make. I mean, and so as opposed to the, let's say, semiconductors or something else, basically, you know.
So, when I think about something like this, I figure that probably if it wants to be quantum, it's probably going to be at lower temperature. But I have this prejudice in my mind that organic stuff doesn't work at low temperature. Is that just a prejudice?
No, actually, this stuff, right? I mean, you're right in some extent, right? Because in this system, what happens, I have tons and tons of temperature-dependent data that I can share with you. The thing is, the actual redox process where you're exciting electrons, they're transporting electrons across the ligands, that process is not at all affected by temperature. Actually, it works, almost with a certain degree of temperature independence, actually. But what the hysteresis process that we see, which involves this counter ion motion, that is very, very temperature dependent, because the counter ion thermal activation energy is very, it's pretty high compared to, KT, and therefore by the time I get, like, for example, why do I see all of these steps and all of this weird behavior? And all of this has to do with the thermal activation energy of the counter ions, basically. And so I'm reaching these are all done at a temperature range, which is way below room temperature, actually. And that's where a certain temperature range in which we see all these phenomena, basically. And so this is related to the counter ion dynamics and its temperature dependence, basically. So my feeling is that so if you involve the counter ions, and then these devices will have to work, at higher temperature than I would say something like liquid helium temperatures. But for example, you take, let's say, the qubits that are made of, let's say, the defects in diamond, for example, right? So, but in that system, of course, you get to see the very long lifetime only when you get to very low temperatures.
Yeah,
I would agree with you. Yeah. So it'd be interesting, actually, to play with this system to come up with some ways to, there may be a qubit that doesn't involve the counter ion, but involves only the just the main metal and the ligands. Maybe something could be thought of there. Yeah.
What about the coherence?
Yeah, I mean, that would be another thing which would be interesting to measure. One thing I didn't mention the data is the optical data in the system, where in the off state, this molecule is very, very luminescent, actually, photoluminescent. Whereas in the on state, it's very dark. Its photoluminescence is really bad. In other words, it's exactly the opposite. In other words, the less conducting state is very photoluminescent, where the conducting state doesn't have much photoluminescence at all. So actually, we have an optical readout in this system. And for example, if we build an M by N memory of some sort, right? Build a crossbar type of switch and so on, we can actually not only measure it electrically, but also measure it optically, basically, because the on and off have completely different photoluminescent properties. So you shine a light on this whole thing, you can actually see the circuit light up, basically.
Cool.
So
Thanks.
Okay.
I think one of the interesting things is we really want to do some interesting image related experiments with these things actually at some point, basically. So there's a lot to be done. I mean, we're just scratching the surface with this molecular system.
I'm sorry to jump in. I think that Mesom has been waiting very patiently to ask a question. So maybe we can come back to this if we have more to discuss.
Okay.
Yeah, I was just wondering what you think the sort of status and prospects or challenges are for taking what you have here with these memristors and then connecting them all together and doing some deep learning, something like that.
Yeah, actually, okay, because of lack of time, I skipped some data, but I'll show something very interesting. This was also related to some of the questions someone else asked. Okay, let me get. Okay, so this is another device, okay? And this device actually has a characteristic. Somebody asked me this question, whether if you go in the negative direction, will you see more permutations, right? Remember? And you can see this device does this. It comes like this, then goes like this, and then it does something like this, like this, like this, right? This is a very extraordinary device. We've just submitted this to Nature, this paper. And what with this device, it turns out that you can essentially ask many queries. And if you look at the different voltage states as your, essentially your boundary conditions that you're establishing in essentially asking questions, right? Then what happens is that you have, with a single device, it turns out that we can actually do 71 different decisions using a single device like this, basically. To give you an example, in a CMOS device, you have an on state and an off state. So it's a binary device. So in terms of decision, I can make two types of decision, adding yes or a no. Whereas in this device, I can put 71 different conditions, and there are 71 different essentially decisions possible in a single device like this. And this is something which is really extraordinary. And we've been working with Stan Williams in Tamu, and he's brought into it one of the original guys who wrote the software for the Nintendo or whatever. That guy's like, so the guy completely went wild on a device like, he says, I want to write the compiler for this. I really want to do this, and so on. So what I'm trying to say is we are completely in a new terrain where I have zero expertise in understanding these decision trees and all this stuff, right? I mean, I really need to develop a very broad-based collaboration with people with a completely diverse set of expertise, right? I mean, we need to bring in people from the AI/ML community to us, right? But they themselves won't know what to do with this until there's someone who knows how to take a device like this and the electrical data that I get out of this device, how do I use it? And that would require a compiler that would say, okay, this is how I feed my data in, and this is how I do my computation with these devices, right? So someone needs to build in that interface, basically, right? So we're putting that network of people together. That's one of my hopes. That's part of the reason why I split my group into kind of like a part that will work at NIST and a part that will work at Oklahoma, because the one at Oklahoma will not have the access to the network as the one at NIST, basically,
Do you have any examples where you like the system is learnable, like it can, based on some training data, it learns parameters, and the kind of more standard, abstract way that machine learning goes?
Right. If you look at the history lies in looking at where oxide memristors have gone. Okay, so already, a lot of people are using oxide memristors and building learning circuits and so on with oxide memristors for, image recognition and so on. There's edge recognition, for example, is an important thing. So those kind of stuff, work is already taking place. Okay. We are actually building devices which are way beyond these oxide memristors in terms of capability. So it's going to be very interesting for us to build the right community of people around us to, take progress to the next area, simply because we don't have that expertise, basically, right? So we need to form that community, actually.